Hello, my name is Juuso Haavisto, and today I'm presenting this paper on GPUs and network functions and how we can integrate Vulkan with Kubernetes. So first of all, we could start with dissecting the title. So most people are probably very familiar with GPUs and the way we can think about them in terms of network function virtualization is to consider those as parallel computers that just happen to be initially developed for graphics, but nowadays we use them for a lot of compute-bound and like tensor computation applications such as machine learning and data science applications. And then network function virtualization could be thought about as this way of kind of like putting Linux software on network equipment. It's not precisely correct, but kind of like thinking towards this softwareization of network equipment, nonetheless. One example could be eBPF, which we do not cover here, but as for one example, and then for Vulkan is the next concept, and that could be considered like a Docker, but for GPU programs. So Vulkan is a graphics API, but it also has these compute capabilities inside of it, and moreover, it's an interoperable in the sense that what we will see in later chapters. And then finally, Kubernetes is a container manager system, or maybe more commonly called as a orchestration system. So basically, nowadays in industrial settings, a very common way of running container applications and then managing and scheduling of those. So to really understand kind of like what is this Vulkan thing, it's a quite central topic in this research, and for that we have to understand a bit about what are the other options and how we ended up with choosing Vulkan. Well, first of all, we can kind of like classify or categorize these APIs in many different ways. One of them is operating system specific APIs, as seen on the left. So APIs like Microsoft DirectX and Apple's Metal can do both compute and graphics applications, but these only work on certain platforms. So Microsoft DirectX works only on Windows, and Apple Metal, unsurprisingly, works only on Apple hardware, such as iOS devices and then the M1 computers. Then on the right, we can see manufacturer-specific APIs, such as the NVIDIA CUDA. So this is meant for compute applications only. And this is pretty much the current de facto way of running some compute applications on GPUs. So usually when you want to run some machine learning application, you will see that most people are using NVIDIA CUDA. But here in this research, we actually do that with Vulkan instead. So Vulkan is now part of this platform agnostic, or other way of calling it would be interoperable APIs. So for those, we have a bunch of APIs. For compute applications, the commonly known one is OpenCL, and then since I think it's 7 years ago, we now have Vulkan, and then on the graphics side, for the platform agnostic ones, we have OpenGL. OpenGL can also sometimes be kind of like tricked into doing compute applications by kind of like introducing your problems as shading problems, but that's a bit more tricky. But anyway, we can see that if we choose Vulkan, we will get the computation capabilities that we want, maybe graphics, maybe that's relevant as well later on, but moreover, it's platform agnostic, so you can run this on anything. You can run this on Windows, you can run this on NVIDIA hardware, you can run this on AMD, M1, iOS, everything goes. So and then another way of kind of like thinking about the current state of affairs is regarding Kubernetes. So running GPU applications on Kubernetes is very constrained, and to introduce new functionalities to network function virtualization on that front would be something that extends on the current capabilities. So currently it only supports AMD and NVIDIA graphics cards, and then there are some restrictions about what applications can use those and how those applications can reach those devices. So basically containers do not share any GPUs. So you cannot have a single container which is kind of like trying to split up a single NVIDIA GPU into two parts, and moreover it is not possible to request a fraction of a GPU, even though it's possible for a single container to request more than a single GPU. So next up we get into the Vulkan and Kubernetes overview. And the main point here is that modularity facilitates composability. So on the right side you can see this the topmost figure called the overall architecture. So here basically we describe our system in which we first take an array language, we translate it to something called SPIR5, which is this intermediate representation format understood by Vulkan. So Vulkan only understands this SPIR5 format, and then Vulkan then communicates this information to the GPU. But moreover, like our contribution is then creating this loader program or Vulkan loader program, which communicates through a container network interface to Kubernetes and fetches information from Kubernetes and back through API. And for here we use kubeRS. But the remarkable thing here is that the Vulkan is very much like a car engine, but in the sense that Vulkan is not a complete car, but instead the engine comes in parts. So you could say that Vulkan is very hard to build and build on, but if you are able to do it, then it will allow the programmer to retrofit it into new kinds of environments and applications, such as Kubernetes here. And as previously said, some upsides is that if you reach this state, if you are able to make it work, then Vulkan will work on any GPU. So that's more or less the guarantee that they are trying to give to the developers. And then for the Kubernetes part, what we are also able to reach is because of this engine-like how would I say it? Engine-like way of having the things come in parts. It allows also the containers to share GPUs and then also request a fraction of a GPU. So that's an improvement. And then also on the right hand side on the bottom left you have the other figure, and this has it kind of like describes the Kubernetes cluster situation, that supposing we have the architecture from the top side, then how does Vulkan really fit here, or how does the GPU instance fit here? So there we can see that the GPU instance is on the blocks, it's the middle block, and the way the GPU instance differentiates from the CPU secondaries is that the GPU one does not come with CRI, which stands for Container Runtime Interface. So essentially the GPU instance is not able to run containers. Instead it focuses on running Vulkan and the GPU NFVs on top of Vulkan. And instead what it does is that it uses kubeRS to communicate through the container network interface with the primary node, which then facilitates the communication between each of one of those nodes. But then, to not make things too easy, is that the interoperability is not free. So as I mentioned briefly before, is that to use Vulkan in an effective way, you have to have a vast understanding of the Vulkan pipeline. And there are many ways to create a pipeline. And that was one of the contributions we did in this paper, was to create a compute pipeline for Vulkan, which can be then integrated with Kubernetes or other applications. So, but that also included this remark, which is given on the left-hand side. So one of the Vulkan pipelines is on the right, and then this remark of how we can then integrate Kubernetes in practice into this is shown on the left. So essentially, in a typical situation, you describe these services to Kubernetes, and that basically creates this correspondence between pods and the network routing. But on the right, you can see the way that these GPU network function virtualization applications can be instead scheduled. So essentially, the point is that we use metadata to pass in the name of the service and then the Sphere 5 application. And that's base 64 encoded. And then we specify some ports and this endpoint system, which then binds specific applications to specific ports of the GPU node. And because of the previous integration with the network interface, what happens is that we are able to use the normal Kubernetes abstractions to also expose these services within the Kubernetes cluster, which actually are made of GPU applications. And then the way that this can be then made even finer in granularity is then looking at the Vulkan and Sphere 5 as this way of a hierarchy. So what Vulkan is actually just a way of scheduling applications. So many times people talk about Vulkan and Vulkan kind of like executing applications, but that's not really how it works in some sense. Instead, there's this scheduling part which includes GPU, how you use a GPU and how you use queue families and how you use queues. We do not go too deep into this, like what these are, but there's a figure on the right side which basically shows that these GPU queue families and queues basically vary between different devices, and that has some implications regarding the performance of applications. And then on the other hand, then you also have the execution part in Sphere 5, which is a complete another thing. But essentially, more or less, when we think about the Kubernetes situation, what we can also do later on is that we can target individual queue families or queues and GPUs within a single node to execute the computation. So this goes back to the concept of the engine. So because the engine comes in parts, we can also go a bit deeper into the GPU and expose these individual threads in some sense of the GPU to be scheduled by individual applications. And then this kind of like goes then more into the approaching the case study application we did in this research, which started from this kind of language trilemma thing, is that each of those APIs that we covered previously have their own canonical language, or kind of like this, they require some language to be fed into these APIs. And in Vulkan's part, that is called Sphere 5. But when writing this paper, it seemed like writing this Sphere 5 straight out was a bad idea, because essentially it's an assembly language. But so writing it eventually is required to use larger set of Vulkan specific features, but then the idea was to model it first in some other language. And kind of like choosing such language is a good notion to know about this language trilemma. So the idea goes that languages such as CUDA and Futhark are productivity and performance orientated, and then languages like OpenMP and C are performance and generality orientated. And languages like Python, MATLAB, and Julia are productivity and generality focused. So basically, a language can only choose 2 points of these 3 things to really focus on. Otherwise, you would have a hammer, I guess, because everything would look like a nail in that programming language. So we approached this with APL. APL is a language from the 1960s, and the point is that APL is a language which it cuts away a lot of the generality of the programming language, and instead what it does is that it focuses on programmer productivity and performance. So the way, or what is lost is that APL only works for rank polymorphic arrays. So there's some examples on the left hand side. So 1 + 1 = 2, but then the sum operation is actually rank polymorphic, so it can operate on various ranks of arrays. So on the second part, it then 1 plus some vector actually does it sums the single value over each of the elements of the vector, and then the same thing for matrix. So basically, it's just it's a way of like hiding loop constructs. But what it allows is to approach GPU programming from a very nice way, since a lot of it is about parallel computation, and APL, by kind of like it focuses to use these inherently parallel functions. Then what is left is very, very verbose, or like not verbose, but a simple way of expressing more complicated array algorithms. And we did this for a random forest prediction. So it was a part of our network classification work of a previous study. So effectively, we took a bunch of Python's scikit code, we turned into APL, and that APL code can be seen on the right. And then we translated this by hand from this APL thing into a SPIR5, and then we ran the SPIR5 on Vulkan. And essentially what it came down to be is to do this random forest binary tree traversal in APL, and we found that we were able to improve on the CPU baseline, which is now Python. So basically, once you go deep enough in Python, you will find that there's a bunch of C code in there. So that took 380 milliseconds on this Intel Core i7 processor, and then on GPUs with SPIR5 it took varying amounts, saying that in each case it was faster, but then there were some things that we will talk in this slide. So yeah, one of the kind of like, I guess, surprises was that the GPU was only slightly faster than the CPU. Someone might predict it to be an order of magnitude faster. But on the other hand, the tree traversal algorithm doesn't really render itself to huge parallelism, since you can only traverse a tree essentially by at a single point at a given time when it's yeah. So then another thing was that NVIDIA was slower than AMD, but this in our case was most likely due to the fact that the AMD was newer and faster card. And then another point is that the Apple M1 system on chip has a very fast memory copies. So even for this kind of application, the most overhead comes from memory copies. So SoC systems, so system on chip devices with integrated graphics cards, are always they're kind of like doing things a bit faster, since they do not have the same overhead as the discrete ones. But once the discrete cards start, those go very fast. And this is also a good demonstration of the fact that the single application, or the single SPIR5 code, it worked on NVIDIA, AMD, and Apple M1. So then the future work is essentially around scheduling and execution. So we mentioned before about these queue families and queues. It would be nice to expose those for a finer scheduling granularity, so that if you have some CPU applications, you can then chain and reserve resources in this very fine granularity. And on the other hand, on the execution part, it would be interesting to see if it's possible to like split a single job into multiple ones. You could think that if there is some very simple matrix operation, like let's say some reduction of 3 rows, then you could probably split those 3 rows into 3 tasks and distribute them over to the network. So essentially, it goes towards distributed computing, and that's more or less what I've been working since. So the conclusions is that we integrated Vulkan into Kubernetes to run network function virtualization applications. And then we also, as a part of this study, we created an open source Vulkan program loader, and there's a link to it. It's written in Rust, and you can also find the random forest prediction algorithm from the examples. It's called RF. And then we also did this case study application and found that we did improve over the CPU baseline. And in the future work, we will address finer scheduling granularity towards doing even more efficient scheduling. Thank you.